Alright, here we go. This is the Lab 4 Uniform Circular Motion in Gravity online video write-up. For our lab objectives, I came up with to gain a deeper understanding of uniform circular motion, especially in how it relates to centripetal force, and to learn how to apply the inverse square law to a real-life situation. I would add a third to that, the gravitational field, falling in a gravitational field, just learning those characteristics of that and how to apply it to a real life situation. Hypothesis, it was pretty simple. I hypothesized that a lot of errors would be made during this experiment just because it seemed harder than the others. Alright, pre-lab questions, answered those on the right on the document. Alright, for part A, centripetal force, I made the apparatus, 2 weights, spun it around 15 revolutions per radius, marked down the times, found the periods by dividing by 15 revolutions, frequency, then used the equation in pre-lab question 2 to find the expected value, and then found the percent errors of those, which were pretty big. First confirmation of this, here's a short video of me doing it. Spinning them around, it's kind of hard to tell. And then part B is also in this, so I measured the height and then dropped it 9 trial of each object. And then I got Micah's help to measure out the light. We're kind of blocking it, so it's hard to see, but that's what we were doing right there. Alright. So for post-lab questions, let's solve physical quantities for A. Well, first I'll go over data for part B. For part B, just had several objects, 5 objects, dropped them a total of 9 times. Here are the objects list. This is the height I dropped it from. Right here, average fall time calculated on another page on the scrap paper. I calculate average or acceleration. Here's my work for A, finding the periods and then the percent errors right there. That's the equations for A. And then free fall time average for each of the objects is all right here. Yeah, and then calculate acceleration is right here. So those are all that. This is for part C. Which part C, took a cup, put it over a flashlight, stuck back 5, 8, 11, 14, 17, and 20 centimeters each. Came up with an intensity. I'm not sure if this is accurate or not. Diameter of the light, measured that out in centimeters. And then this is how I found the area, just using the traditional area equals pi r squared, but doing the pi diameter divided by 2 times r squared. So that's how I found the acceleration or area, beg your pardon, for each of these. And then for lab questions, let's solve the physical quantities that affect the value of centripetal force. So the values that affect centripetal force are the mass of the object, the velocity, and radius of the circle as it spins around each of those. The line to the distance, velocity, speed at which it's moving, and direction, I guess. And then the mass of the object. So I had quite a big difference in error between each experimental versus the expected periods in part A. I counted this to probably improper operation of the apparatus. My weights are a little heavy, and I was trying to spin it around, and I'm not sure they were balancing out right. So probably just a systematic error or operation error on my part. So yes, a shorter radius allowed for a faster speed, gave rise to shorter period, vice versa for longer radius. For the circle, I drew a circle having the velocity going in that direction, so that it's spinning counterclockwise. There's a radius, the centripetal force, centripetal acceleration, centripetal force pointing inward and outward, but acceleration pointing inward because it's parallel to the velocity. Or sorry, not parallel, perpendicular. So then the average, this is a little messy right here, but average velocity, angular velocity, and then centripetal acceleration for each radius is calculated here, just using V equals RW, W equals V divided by R, and AC equals V squared over R, all to calculate all of these, which there's the final value. Hypothesize that the force causing this vertical acceleration in the swings at an amusement park is in the tension in the wire that connect the swings to the top of the structure, and the chain's velocities will increase by a factor of more than 2 because if the angular velocity is doubled, the radius of the circle increases. So with an increasing radius and angular speed, the velocity factor would double, so it would be more than 2. For post questions B, part B, each rate of acceleration is pretty different compared to the others, mainly due to the difference in shape, size, and density of the objects I chose, making their acceleration expectantly different. The equation would change from df half at squared, or acceleration equals d, to df time squared to gme because of the Earth having that gravitational constant, the Earth's radius, and then the mass of the Earth. So change from that to that if you put it on an Earth scale, being that far away from Earth anyway. Falling objects fall slower when air is present because the air acts like an obstacle, somewhat of a barrier, depending on the initial drop speed and surface area of the object. So each area is each object is getting acted on differently by air depending on its surface area, how much air resists. Yes, the forces acting on both objects in the same way. However, we take account of the natural attraction between all objects on Earth. Smaller objects are going to gravitate toward and accelerate towards larger objects, other than the other way around. So large objects don't go towards smaller objects. Smaller objects go towards bigger objects. So while it is the same force being applied to each mass, those with greater mass are going to pull the smaller mass more. Verified by the Earth and any object that drops towards the center. How does Newton... Okay. Newton understood inertia by simply that if an object is at rest, then it's equal to its resistance of being moved through equal to all other objects also at rest. So in order to move, an unequal force would have to push it, and therefore would be larger for massive objects and smaller for less massive ones, which explains that the smaller ones in a gravitational field don't accelerate, or bigger ones don't accelerate as fast as the smaller ones. Okay, for part C, finally, holding lights. The farther the light source was from the wall, the more the circle of light covered, so bigger surface area. However, the brightness was most intense up close and least intense the further back you got, or lessened as you far back. The light intensity represents the original area in relation to how it changes over time. So covering that initial area versus further back. Observed the area of the circle increased as the intensity decreased. It's inversely proportional. Area of circle is inversely proportional to the intensity of the light. There it is in equation form. For 5 and 6, here's this answer right here, the scatter plot with the line of best fit, distance being the independent, intensity being the dependent value. And according to inverse square law, the ratio of distance to surface area is 1 to 2. For every doubled surface area, for every doubled distance, the surface area is going to cover 4 times that. The intensity is inversely related, so it's going to be get less by a quarter, because inversely proportional to the square of the distance. Despite all this change, however, gravity remains constant and does not affect light. Yep, so that's pretty much it. Thank you, and goodbye.